Hello, everybody. My name is Carlos Ramirez, and I'll be talking about series in economics and finance. I'm currently a math major, and I'm hoping to be a math professor one day. But for that field of work, I'm obviously not able to dial in on a single topic for this presentation, so I decided to go with my next option, which would be to go into finance. I'll be diving in more specifically to geometric series and how they're used for everyday things like loans, retirement planning, and evaluating investments. Of course, we all know what a series is, so rather than going on and explaining to you what they are, I want to talk about why these have real world value and how they're used in finance and economics. In these fields I'm here to talk about today, we constantly deal with money that flows in and out over very long periods of time. These payments could be seen through loan repayments, monthly pension checks, or just future investment returns. The problem with knowing what to do with your money and making these incredibly hard decisions is how do we even make these decisions today about things that will happen over years or even decades? This is where the idea of convergence becomes very useful. If we can model a series of future payments, even an infinite series, and show that it converges, we can turn those future cash flows into a single useful number. That number helps lenders, investors, banks, and people trying to retire make stable and smart financial decisions. When we say a series converges, we mean it settles on a final value, sort of like a cap or a limit. If you keep adding smaller and smaller amounts, eventually you just continue adding zero. In this picture I added, it does a great job of showing what that means. The amount you're adding keeps getting smaller, which doesn't change the total. In finance, this is important because it tells us we can actually calculate a finite usable number from endless streams of payments. Without convergence, the math would be meaningless. It would just continue to grow forever, so convergence gives us a way to control the future. Well, why do these geometric series work in finance, and how could they be so useful? These are especially useful because they reflect how real payments work. They're regular and they follow a pattern. For example, mortgage payments happen monthly. Retirement checks also come monthly. If we factor in interest or growth, each payment in the future is slightly less valuable than the one before, and that shrinking value is what gives us the geometric pattern. That's what shows us convergence, giving us a predictable value. So when we model loans or investments using a geometric series, we're capturing the structure of how money actually moves in real financial systems. And if the series converges, meaning it adds up to a stable value, we can use it to calculate important things like present value, total cost, or long-term returns. So I've already talked a little bit about how these series are used in finance, but here are the three main topics where I'm going to focus and how geometric series can be used in them. First, we have loans and mortgages. These series can be very useful in figuring out how much you'll pay over time and what they'll be worth today. Very useful for people trying to invest in properties. Next, we have retirement funds and annuities. These series help planning how much you need to invest now to receive the payments you want in the future. Next, we have investments. The series help us evaluate the long-term value of things like stocks, bonds, or dividend income. All of these things, geometric series let us analyze money that's moving through time and help us bring it all back to the present value. I want to dive a little deeper into the mathematical explanations of how these series actually work and how they can help determine the costs or the value of your investment accounts, mortgages, or retirement accounts. Starting conceptually, when you make regular payments, like a loan, each future payment is worth slightly less because of interest. This creates a geometric series as seen on the screen. When putting in your values, you're given your present value, and that gives you what your property is worth today. As you continue to make these payments, we see that the bottom increases. These payments shrink as they're pushed further into the future, and the sum converges to a finite value. That value is the present value of all those payments and how much they're worth right now. This lets banks and planners understand the cost or value of long-term money flow using a single number. So now, let's apply that same principle to a loan, something long-term like a mortgage. Obviously, we all know how a mortgage works. The bank gives you money and you pay it back over many years. In order for the banks to give you this money, they need to figure out how much they can actually give you. They need to calculate the total value of your future payments, and that's where this formula comes in. Similar to the last one, the formula gives you the total present value of what the loan would be worth. P is your monthly payment, I is the interest rate per month, and N would be the total number of payments. The formula compresses a long series of payments into one clean value. It helps banks make sure they get their money back and helps you understand exactly how much you're paying for the loan. An example of this that makes it a little bit easier for us to conceptualize using numbers is, let's say you take out a $200,000 mortgage with a 4% annual interest rate, and you make payments for 30 years. It would end up being 360 payments in total. The bank would use this formula to figure out exactly how much those 360 payments are worth today. We know with interest, you'll end up paying more than $200,000 over time. Because of that interest, the present value is what the bank actually lends you today instead of just the $200,000. So this formula helps both you and the lender understand the full cost and value of the loan. This formula obviously looks different to the one we're used to seeing, the standard geometric series. But in that standard form, you're multiplying by the common ratio r. But in finance, we work a little different. It's more backwards. We're not actually adding future payments, we're discounting them to see what they're actually worth today. So instead of multiplying by r, we're dividing by the powers of 1 plus I, which is our growth factor, or what they call in finance our discount factor. Now this part here, inside of the parentheses, that's the sum of a finite geometric series, but just flip for discounting. We raise 1 plus I to the negative power, because the further out in time the payment is, the more we discount it, which means that more it shrinks in value. This 1 minus part is what gives us the stopping point. It cuts the series off after n terms. When you multiply that entire thing by p, it gives you one single value that sums up your entire payment timeline into that single value. With retirement funds and annuities, it's a similar step as calculating loans, but instead of paying a bank, the bank wants to pay you, like in retirement. When retiring, you want to receive regular payments over many years. But how do you know how much to invest today to actually make that happen? We use the same formula, but just in a slightly different way. PV would be the lump sum you invest, P is the monthly income you want, and N would be how many months you want it to last. This helps people trying to retire and financial planners figure out exactly how much money they'll need now to support a steady lifestyle later. The reason this math is so important is because it gives us confidence. It lets us make financial decisions with solid predictions. Whether you're retiring, borrowing money, or investing, you can use these formulas to know what you're really dealing with financially, and you're not just guessing. Now to explain this formula, it's obviously the same one as we saw on the last slide. We're just flipping the context a little bit. We're still summing a geometric series, and we still use 1 plus I to the negative n power to reflect how the payments shrink in value over time. But instead of asking how much can I borrow based on the payments I'll make. This formula helps us solve this for retirement funds, letting us know how much do I need to invest now to create those future payments I want when I retire. It's the same structure and the same math, but just a different direction. Creating a scenario, let's say you want to retire at 65 and live off $3,000 a month for the next 25 years. That's a lot of money that you need saved up, nearly $1 million in total. This formula we use helps us figure out how much you actually need to invest today, but what happens if you underestimate that? You would be running out of money in your 70s or 80s, which obviously is not good. That's why when financial planners use this formula, they build safety buffers. They'll tell you, okay, what if interest rates drop, or what if you live longer than expected? That's what's so great about this formula, is that it's very flexible and you're able to plug in different numbers and you'll get different plans. It's like you can simulate your financial future. Finally, we're going to be talking about investments, especially the ones that pay returns in the form of dividends, like stocks or bonds. Since the payments are ongoing and never stop, we use a simplified version of the geometric series formula that we showed previously. P is the return per period, like a dividend, and I is interest rate or discount rate. This is called a perpetuity formula, and it tells us the present value of a constant, never-ending stream of money. Investors use this to figure out what an asset is worth today based on what it will keep paying out in the future. For investments, this formula looks way simpler, and it is, but it's still based on a geometric series. If we took the normal infinite geometric series, which is p plus p over 1 plus I, plus p over 1 plus I squared, that continues on forever, we would get this formula. It's because the infinite geometric sum converges to a equals 1 minus r. Here a is p over 1 plus I, and r is 1 over 1 plus I. So if you plug those in and simplify, you end up with this formula, p over I. It's not really a shortcut, but it's the limit of the geometric series when the number of payments goes to infinity. That's why I use for things like company valuations, where income is expected to last forever. Before wrapping up my presentation, I just want to go over the key takeaways that we've gotten from this presentation. Geometric series are used every day by banks, planners, and investors. They help us bring the future into focus, and thanks to convergence, what we look for when we do series, we can turn endless payments into usable present values. And of course, here's a list of all my sources. Thank you all for listening, and I hope you all have a better understanding of geometric series inside of finance.